Anish, back to your place today. For the whole day, you are supposed to be sitting there. Sorry, I cannot bend my rules. Go. Right hand up. Yes. Yeah, the rule applies to everybody in the class. I told you. Have you followed? Once, if I find anybody disturbing, you will be all sitting in different places. I've given you enough time to settle down. Okay, right hand thumb rule once again. Page 199, the last line, last few lines. Right hand. Yeah. Yeah, we have read it. So what did we say? If this is a conducting, pay attention. Pay attention now. Everyone pay attention. Here. Okay, so let us say that this is a conducting wire. Okay, and remember that it is a straight conducting wire because there is another wire we are talking about the loop. So even the words, I want you to pay attention to the adjectives. So it is a straight current carrying conductor. You understand? If this is a conductor and there is no current passing, it will not develop a magnetic field. Only when there is current which is passing through the straight conductor. So what should we write? It is a current carrying straight conductor. Can you follow? Okay. So if we are having I, that is current which is flowing in this particular direction, obviously there is a magnetic field which develops around. How does it develop? Here like this. And how can we find out the direction of this magnetic field? By using our right hand thumb rule. So imagine you are holding the conductor in your right hand such that the thumb points in the direction of the what? Current. And the curled fingers show the point direction of the what? Curled fingers will show the direction of the magnetic field. It shows the direction of the magnetic field. So your magnetic field is in this direction. So with respect to the current, the direction of the magnetic field is always anti-clockwise. Have you followed here? Okay. First we'll write down this statement in your notebooks and then we can continue. Take down right hand thumb rule in your notebook. Page number 200. Ready? Imagine, we start by saying that you are imagining holding. Okay, from there itself. Imagining that you are holding. Imagine that you are holding a current carrying straight conductor straight conductor in your right hand such that the thumb points in the direction of what?
Towards the
Direction of the current. Such that the thumb points in the direction of the current. Next line, write down continuation actually. Then the curled fingers. Curled fingers show the direction of the field lines of the magnetic field. Field lines of the magnetic field. So what is this rule called?
Right hand.
Right hand control. Yes. Okay. So because it becomes very useful for us to find out the direction of the magnetic field. Look at the last thing there. This is also called as Maxwell's corkscrew rule. Suppose you want to, let us say, hammer something, you want to put up a poster or something, or maybe you can drive a nail, or you can also use a screw. So when you're using a screw, what happens is you're driving the screw inside the wall, but the direction where you're actually turning over, that basically gives you the direction of the magnetic field. It is the same thing as this. Have you followed? Look at the last few lines there. Ekta method, bottom here. This rule is also called as Maxwell's corkscrew rule. If we consider ourselves driving a corkscrew in the direction of the current, then the direction of the rotation of the screw is in the direction of the magnetic field. Okay? So along with the right hand compass, put a star in your notebook and also please write down, also called, this is for you to remember because it's so small that you might forget. This is also in your notebook, please write down, also called Maxwell's corkscrew rule. Maxwell. Here. Here, it is given here. You don't have to write anything here. Yeah. Okay. So let's see what this experiment is once again. Pay attention. Why am I drawing the whole thing again? Is because such type of questions will be asked for your exam. Okay. A diagrammatic question will be given. You are asked to find out, okay, probably what your observation is and what the observation is about. What is your interest? So suppose you are taking a cardboard, okay, and you are having a wire which is running through. Is that okay? Can you imagine what it is? This is a cardboard, you're making a hole and you're passing the wire like that. Will it have a magnetic field? In this diagram, will there be a magnetic field? Yes or no?
Yes, no.
Why? No, why yes? There's no cell, nothing. There's nothing there. So there's no magnetic field. So what should I do? Immediately I have to put a connect. Now I will also have
A switch.
maybe I can have a switch and maybe I have closed it. Which is the positive, which is the negative? The bigger line, positive, this is the negative. How is the current flowing?
Positive to negative.
So how do we know? Once again by drawing arrow pins. Okay, so the current is going in this direction. Correct? How will I know the direction of the magnetic field? How will I know the direction of the magnetic field? Will there be a magnetic field around?
Yes.
Yes. In which direction? Is it like this or is it like this? How will I find out? By using right hand thumb. So this is the direction of the current. So I'm holding my pen or pencil in my right hand and it is in this direction. So the magnetic field is in this direction.
Yes.
Sorry,
Anti-clockwise.
anti-clockwise with respect to the current. With respect to the current. Okay, now my question is, Rashika, suppose I want to increase. Now I know what is the direction of the magnetic field. I want to increase the strength of the magnetic field. So what should I do?
Bring the magnet
My question is, how can I increase the strength of the magnetic field? Start, come on.
by getting closer to
By getting closer to it. By getting what closer to what?
Increasing the reducing the length of the wire, increasing the potential difference.
By increasing the potential difference here. So what happens?
The magnetic field becomes stronger.
What is this magnetic field doing? How is this magnetic field developing?
distance from the point.
I'm asking you a question again. Listen to me first. Shh. Listen. If I take it away, will there be current? No. If there's no current, there's no magnetic field. Okay, so the magnetic field is due to what? It is due to the current that is flowing. Now my simple question is, how can I increase the strength of the magnetic field?
Brings your magnet to like towards
the
the magnetic
magnetic
field.
You are perfect here. By increasing the current, you increase the current which is passing here, this field will get more. Strength of the magnetic field will get more. Boys, you have all missed out. I'm not going to repeat what I've said. I'm sorry, I don't know. You continue to talk, I have no problem. The next thing is I'll open the door outside. That's all. So how can I increase the current here? Instead of putting 1, I can put a battery or cell. So instead of putting here 1, I can also put 20. Do you understand? So I have increased the potential difference. More, you would also write, potential difference is more current is there. If more current is there, obviously the strength of the magnetic field will keep on increasing. Is that okay? Once again, these are concentric circles. Did you notice that these are concentric circles? Now my question is, suppose I have brought a compass needle. Okay, this is a compass needle. It's very far away, and obviously it is in the north-south direction. But if I'm getting it closer and closer, will it still show in the north-south direction? It will get deflected. Why?
Because it's coming in interaction with the wires magnetic.
Is this a wire?
So
Coming under the influence of the magnetic field. So the moment it starts coming, there's a deflection. Did you see? Why? Because it's coming under the influence of this magnetic field. Is that okay? So one way of increasing the strength of the magnetic field is by increasing the number of cells that you have taken. Therefore, the strength of the magnetic field is also increased. Now my question is, look what I am doing very carefully. Now what happens? What did I change now?
There's no switch.
Okay, I'll put a switch, no problem. I can put a switch.
the direction.
The direction of the
Very
current.
good. Very good. You have noticed that the direction of the current has changed. Yes. So now the direction has changed. The current also has changed, and now it is flowing in this direction. So if the direction of the current has changed, what will happen to the direction of the magnetic field? Will it remain the same?
No, it will
Change
like
the
turn
opposite.
towards the
Opposite direction. How will we find out which rule? Which rule? A thumb rule, right hand rule. Now how will we do it? This way, because obviously the current is flowing in this direction. The current is flowing here, the direction of the magnetic field is going to be in this direction. Did you follow? Okay. So such simple type of questions are asked, but don't mess it up. All that is important for you to recognize is this part. This is very, very important. If you know in which direction it is flowing, you can find out the direction of the magnetic field. Is that okay? Clear? Come on, right up. Ready? Magnetic field, write down the heading. Magnetic field due to a current through a straight conductor. Through a straight conductor. Now just write down, refer figure, what is that, 12.6? Experiment. Activity is 12.5. Okay, but the figure for the explanation of this diagram. Yeah, activity is 12.5, reference figure is 12.6. Chalo. First question. First question. What happens to the deflection? What happens to the deflection of the compass needle? What happens to the deflection of the compass needle? If the direction of the current, in the copper wire is changed. Rishita, read the question.
What happens to the deflection of the compass needle if the direction of the current in the copper wire is changed?
What will be the answer? If the direction of the current is changed, what happens to the deflection?
The deflection will also change.
So what will you write? The deflection will also change in the opposite direction. Right. Okay. Next question. How can we increase the strength of the magnetic field? Not battery power. Correct. How can we increase the strength of the magnetic field? What will you do? Okay, we can increase the current. So you can write by increasing the current, the strength of the magnetic field. Or you can also write the magnitude of the magnetic field also increases. Why is it increasing? As the current, magnitude of the magnetic field also increases because current, yes, because the flow of current is increasing. Because the current in the wire increases. Okay. Now please notice that here in this experiment we have included number of cells, right? But sometimes they may not be as cells. There's something what is known as a battery eliminator. Okay, in the labs where we work, there's something which is known as a battery eliminator. So we can keep on increasing the voltage. By increasing the voltage, obviously the current will also increase. Okay, so that's also perfectly okay. Next. Next question. What happens to the compass needle? What happens to the compass needle when we move it away from the copper wire? When we move it away from the copper wire. Harush, what will be your answer?
Most likely it will change its direction.
Which is the direction?
Yes, ma'am. As the magnetic field is getting weaker.
Okay, now let's say this is girls. If you talk, you'll be there in the last bench or in the first bench. Choice is yours. It will increase. This is the wire. Look at me. This is the wire. Okay, and this is the compass needle. When I brought it, it is obviously getting attracted towards the magnetic field. But when you are moving it away, what happens to the deflection?
It again starts.
See how it is happening. The deflection is more now. When it is moving away.
Yes.
So what will you say? How will you word it? The deflection decreases. The deflection of the compass needle decreases as we are moving it away from the copper wire. Right?
When we move it away from the wire.
Of the copper wire. So what does it prove? What does it show? When I am moving it away, the deflection has decreased. So what does it show?
It is getting weaker.
Correct. Okay. So the strength of the magnetic field or the magnitude of the magnetic field is weaker when you are moving away from the wire. Right? Therefore, the strength of the magnetic field becomes weaker as we move away from what is the adjective I want you to use? Is it only a copper wire? A current carrying copper wire.
Weaker as we move
A
away.
current carrying.
Is that clear? Are we good till here? Nice. Simple questions. But then I don't want anybody to, this is actually very scoring. If you get the words right, it's very, very scoring. Now we come to another very interesting thing. Magnetic field due to a current through a circular loop. Look at the next slide. Yeah. We have now seen what is happening if we are taking a straight conducting wire. Look at me now. This is your cardboard. Pay attention. Okay. This is my copper wire. I am making a hole here. The wire is coming. What is it? It's a loop, taking another hole here, and I'm taking out the wire here. Did you understand what's happening? I have this cardboard, right? I have this copper wire, making a loop, and then it is coming down. Okay, now what are we going to do? Magnetic field due to a current to do a circular loop. Did you understand the construction? We are no longer talking about a straight wire, but now we are talking about a circular loop. What else have to be connected here? What should we do to these two end wires? Obviously, you have to fix it to a cell. Then maybe you have to have a key. Maybe you can have an ammeter, whatever it is. Is that okay? Now what is happening? This is a longer line, positive. So I know that the current is coming in this direction. Pay attention now. Here, when it is coming in this direction, obviously there is a magnetic field here. How can you find out? By using your right hand thumb. Okay, so it is in this direction. So I just draw a small direction to show you the direction of the magnetic field. The current is still flowing here. So it's in this direction. Okay. What's happening to current when it is coming here? It's going down. There's still a magnetic field, but in which direction? It is in this direction. Did you understand how it is? It is coming in this direction. So from here, so it's not like this, it's like this. Is the direction in the same? Current, what is happening to current? Current is flowing in this direction. But when it comes on the other side of the loop, the direction of the current is changing, and therefore the direction of the magnetic field also is changing. Is that okay? So this is what is going to take place at every part. Have you followed? So when this current which is flowing through a circular loop, you have magnetic field lines all over in the loop. Okay. So how can we make out once again what is the strength whether there's magnetic field lines? Once again we are going to put iron filings, and when you gently tap it, what is happening? These are the ones which is arranging in concentric circles. If you look right in the middle, these concentric circles, how is it happening? It's as if they are straight lines, right? Because as you are moving away from it, those magnetic field lines are becoming bigger and bigger. So if you are looking right in the middle here, it appears as if they are almost straight lines. Did you notice this part? Did you notice? That right in the middle, it's almost as if they are straight lines. What happens to these curves as you are moving away? The radius is increasing. And what is happening to the strength as we are moving away?
Weaker.
It becomes weaker and weaker. As we are coming closer to the wire,
Strong.
the strength of the magnetic field is getting stronger. Is that okay? Now my question is, how can we increase the strength of the magnetic field here? By increasing the current. Okay. Is there any other way? Think. Now we are no longer talking about a straight wire. I've given the option of making a loop. I made this loop, and around this loop we find that there are magnetic field lines. So what else can we? This is a copper wire. What else can we? No magnet. I'm not giving you any magnet. One is, of course, you have increased the current. What else can we?
Add more time.
Add more coils. Did you understand? So you have to keep on putting more and more coils. Greater the number of coils, the greater will be the magnetic field around each coil. Okay, suppose instead of one coil here, we are putting 10 coils. So what happens to the magnetic field? It is 10 times it's getting more. Have you followed? So the best method of increasing is either increase the strength of the current, or maybe you can have more and more coils. And that basically gives us an idea of a solenoid. So if you look at figure 12.9, look at 12.9. See what's happening. Is it a single coil that they have taken? They have taken many coils. So this is the card. We are taking a coin, take a coin again. Did you get it? So many coins like that obviously increases the strength of the magnet. Are we good? Did you understand? Okay. Garan, would you like to read?
Yes.
Magnetic field
Due to current of
current to a circular loop.
a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called solenoid.
Where are we? Here.
12.2.
Here.
We have so far observed the pattern of the magnetic field lines produced around a current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it.
Underline. What does it mean? Read it carefully.
We know that magnetic field produced by a current carrying straight line wire depends inversely on the distance from it.
What does it mean? Who can explain the sentence to me? It is inversely proportional to the distance. What does it mean?
Like if the distance increases, the
Magnetic
increases.
Very good. That's what. If you are increasing the distance, the magnetic field is increasing. If the distance is less, then the magnetic field is more. Did you understand? Inversely. Directly, what does it mean? If this is increasing, this also should increase. But it's not increasing. Underline that statement. Yeah. Continue. Garan?
Yes, sir. Similarly, at every point of a current carrying circular loop, the concentric circles represent the magnetic field around it. It would become larger and larger as we move away from the wire. Figure 12.8. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines.
Underline. Why does it appear as straight lines here? Because these circles are becoming bigger and bigger. Okay? So right in the middle, if you look, these concentric circles, they are nothing but straight lines. Have you underlined it in your book? You don't have the book.
I do not. My friends,
So you are planning to take up a CBSE examination this year. When? After the course is over. Then you have to sleep on so many things. I will buy. Next class is on Wednesday. You come with your textbook or you don't come with it. Have you clear? No. Read.
Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop.
So within the loop, obviously it's all in the same direction. Okay, clear? Next page.
We know that magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it.
Underline. Directly proportional. What does it mean?
If the current increases, the magnetic field will also increase.
The strength of the magnetic field. Okay, if the current is increasing, what's happening to the strength? The strength of the magnetic field is also increasing. So that's directly proportional. Underline.
Therefore, if there is circular coil having n turns, the field produced is n times as large as that produced by a single turn.
Stop. Try to understand what the sentence means. What does it mean? What is n number of turns?
It would be equal as the signal.
Okay, come on, yes, tell me. Ayush.
Any amount.
Very good. How do you explain? Suppose there are 10 turns. So what happens to the magnetic strength? Magnetic field? It increases 10 times. If you are taking 50, obviously it is going to increase 20. So there are two methods. One is by increasing the number of coils, and the second thing is by increasing the current. Okay? Right. Underline that statement, it's very important. Last line.
This is because the current in each circular turn has the same direction, and the field due to each turn that just adds up.
Okay. So basically what are we talking about is nothing but what is known as a solenoid. So what is a solenoid? Solenoid is nothing but a copper wire. Look at me. Imagine that this is a wooden, or maybe it is even a plastic tube or even a pencil, right? You're taking copper wire and winding it. Okay? And you're winding n number of turns. This spring-like thing which is formed is nothing but a solenoid. Okay? So how can we increase? The greater the number of turns of the coil, the greater will be the strength of the magnetic field. And such type of, this is the basic idea of a motor. Have you all followed how it is? So nothing but a solenoid is nothing but a copper coil, an insulated copper wire which is wound around any cylindrical object n number of times such that it becomes resembles a magnet. It resembles nothing but a bar magnet. Are we good with that? Okay, clear? I'm going to take down a few points before we start about magnets. Solenoid as a magnet. Your heading, please write down. Magnetic field due to a current through a circular loop. See the heading. So what are the key points that we should make? We should keep note of distances, strength, etc. First point, the magnetic field produced by a current carrying straight wire depends, put a dash, you will fill up this blank afterwards. Okay, depends.
Dash this inside.
Yeah, you will have to fill it up, whether it is inversely proportional or directly proportional. Listen now. Dash on the distance from it. On the distance from it. Magnetic field produced by current carrying straight wire depends dash on the distance from it. What we do it?
Inversely.
Sure?
Yes.
Very good. All of you very good. Inversely proportional. As the distance is increasing, strength is decreasing. Next slide. The concentric circles representing the magnetic field around the copper wire becomes larger and larger as complete dash dash dash. When is it?
And move away. And the magnetic field.
What? The concentric circles are becoming bigger and bigger as
Like the layers are becoming above.
what you first said was perfectly right. As you're moving away from the wire. Correct. Isn't it? As you're moving away from the wire, the concentric circles are becoming bigger. Complete the statement, Raj. Next point. Next, fill in the blank. Okay, I'm giving it to you in the form of fill in the blanks so that you're not only having your notes but also trying to understand what is happening. Right. Next one. When we come to the center of the circular loop,
Center of
the circular loop, okay, the arc of this, big circle appears as dash.
straight.
Correct? Correct? Very good. Next one. The direction of the magnetic field. The direction of the magnetic field in the loop can be checked by using dash rule.
Right hand.
Right hand.
Right hand.
Yeah. No, it's better to use the right hand. Next point. The magnetic field produced by a current carrying wire depends on what? Depends on what? On the current. Basically. Is directly proportional to the current passing through it. Underline that statement. Directly proportional to the current passing through. What is the other way of increasing the strength of the magnetic field here? By number of wires, by increasing the number of wires. The last point is there in your textbook. Please take it down. Okay. If there is a circular loop having n turns, will you get it from your textbook? The last 2-3 lines are there. Read that. Anish, read that. Last 2-3 points.
There is a circular coil having n turns. The field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up.
Yes, please copy down these two. So this is for you to remember 2 points. One is by increasing the current and the second is by increasing the coils. It's okay, these also have to be also. Done? Okay, let's look at this. Can you understand? This is a straight wire which we have already completed. Wire is very sharp. Okay. Did you see the needle here? No, this is one. This we have marked here. This is the first. This experiment here. That's the next part. This we have seen, isn't it? Pattern.
No,
Hey, this is one.
no, this one.
No, ma'am.
Let's see. Yeah, of course we have seen this.
Yes.
Obviously, we have
Yes,
seen it.
ma'am. Yes.
Yeah.
Yes.
Okay. Tell me.
What is this idea?
Let's look at the diagram for a solenoid. Okay. Now, one of the questions which is asked for a solenoid is the diagram question. If you look at the diagram in your textbook, it's very confusing. Look at the diagram there. Girls, see how we are going to draw. Take a wire. Okay, imagine this. Take a wire and you are making a loop around what? Around any like cylindrical wooden piece, maybe even a newspaper roll, like a cylindrical thing. So this is a solenoid. But what is happening to a solenoid? Obviously, we have to connect it to a source of current. So we'll have positive, negative, and in order to increase the strength of the solenoid, I may take one cell or I can take a battery of cells. So if I'm having it as a positive, what is happening? The current is flowing in this direction, passing through the loop. As we are increasing the number of coils in the loop, what's happening to the magnetic field? The magnetic field also increases. Okay? And it's coming down here. So this piece here is behaving like a bar magnet. So what is a solenoid? Solenoid is also behaving like a bar magnet. Just as a bar magnet has the north and the south, this solenoid also will have two poles. But what is the major difference? This is working only with the passage of current. Here it is a natural magnet, okay, and it's a permanent magnet. What happens if you shut the current here? It turns off. It's no longer a magnet. So therefore, is it a permanent or a temporary magnet? This happens to be a temporary magnet, whereas this is a permanent magnet. Can I change the strength of the magnetic field here? Yes. How can you change it? By increasing, yes, by increasing the current or
Adding
more number of coils. Okay, that means the strength of the magnetic field can be changed in an electromagnet. So what is a solenoid? It is an electromagnet. Why do we call it as an electromagnet? Electro?
Because it works on electricity.
Yes, only when you pass electricity it becomes a magnet, not otherwise. Have you followed? So what type of a magnet is it? It's a temporary magnet and it's an electromagnet. Can we increase the strength or decrease the strength here in the permanent magnet? No, we can't do it. Did you understand? There's no way we can increase or decrease it. Decrease it, yes. If you drop the magnet, it's going to lose its magnetism. Have you followed? So I'm giving you points of differences. Think. I've given you 3 points. Or if you think, difference between a permanent magnet and a solenoid. Got
Yes.
3.
Yes.
Got it? Ayush, tell me.
Now, one of them is naturally found, and one of them is only done with the passage of current.
Okay, it's an electromagnet. Second?
The second, electromagnet can have more power.
No, don't use the word power. We can increase or decrease the strength of the magnetic field.
By coiling more
Ah,
or
okay.
adding more.
Okay.
But in the natural one, it
You
remains
cannot
the
do it.
same.
How can we increase or decrease? How can we
By
increase?
adding more cells or coiling it more.
You can say by increasing current also you can say. Okay, stop saying by increasing cells, you can say also by increasing the current, you can increase the strength of the magnet. So what is it? Or what is the similarity? It is similar to that of the bar magnet. Okay. What happens in a bar magnet? Suppose this is the north and the south. You've got the magnetic lines of force coming from the north to the south. Same way here, from north to south. Now how can you make out? If you see those field lines, they are running inside like that. Have you followed? I have drawn only one line for you to understand. In the textbook, they have given you so many lines, so it becomes very confusing. See how the field lines are there? It is coming from inside of the bar magnet or inside of the solenoid and running across. Okay. Now, how can you make out which is north pole and which is the south pole? There's another rule which is what is known as a phase rule. Okay, clockwise phase rule. In a clock, we have these needles in which direction?
Clockwise.
This is clockwise. Okay, so this is clockwise phase rule is what we are going to see. We want to find out what happens whether it is a north or the south. See how I have drawn these two alphabets. Okay, but the way I have drawn it,
The end.
the tail part of it is basically telling you what. If you look at this one, this is running in this direction. So it is your anti-clockwise. Here it is the clockwise direction. So if your winding is in this direction, that is the clockwise direction, it behaves like a south pole. If the winding is in the anti-clockwise, then it behaves like that. Have you followed? Did you understand or no?
Yes.
Like for example, if this is where I have done the winding. Okay, this is the winding. What type? How am I moving my finger?
South.
In which direction?
Clockwise.
Clockwise. So it is going to be the south. Okay. When you come to this, it's going to be in the opposite direction. So it's okay. If one is south and the other one is opposite. Is that okay? Take it up quick. Read this point. Ananya, magnetic field and lead to current in a solenoid. Read that part and then we'll write.
A coil of many circular turns of insulated copper wire wrapped closely in the shape of a
Switching
cylinder.
it off.
Yes, ma'am.
My God, yeah, it is so warm and
Wait. You know, ma'am, behind it, it's very good. Yes, ma'am.
Yes.
I will do one thing. You are feeling uncomfortable there. You sit on this side. Is it because of that?
No, it is turned off now.
You You're okay, right? You people are okay. You come here, come to the first bench, both of you. Ayush and Raj, both of you come here. Go. Varun, are you okay there?
Yes, ma'am.
What about you? Harush, where are you going? ठीक है? हाँ. Another solenoid.
The pattern of the magnetic field lines around the current carrying solenoid is shown in figure 12.10.
Put a star there. It's very, very important. The diagram is very important. Textbook.
Compare the pattern of the field with the magnetic field around the bar magnet. Do they look similar? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid.
Underline. Which point? Which point?
The field is uniform inside the solenoid.
We will not know because we are doing some musty out there.
Already underlined.
Not you. Look at it. Nobody's going to help you now. Are we good?
Yes.
Continue.
A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. When placed inside the coil, the magnet is so formed is called an electromagnet.
Underline. It's an electromagnet. Is that okay? Right. In your notebook, please take down. Okay. Now, first of all, a description of the solenoid. Did we mark it in our textbook? A coil of where is the solenoid?
Coil of circular.
Which page? A coil of, come on, write down. In your notebook, everybody is writing it down in the notebook. A coil of, come on, write down. Many circular turns.
It's called solenoid.
Yeah. Done? Can you find some similarity to that of a bar magnet? Will a solenoid behave like a bar magnet? What happens if I take? Look at the board, everyone. Suppose this is a piece of nail.
Like a magnetic north.
Yeah. Suppose this is a nail. If I get it close to it, what will happen? It will magnet, just as a magnet. Okay, so it's obviously going to cling on to it. Okay. So now my question is, what are the similarities, or what can you talk about the solenoid?
Both are magnetic.
Okay, it's an electromagnet. It's a temporary magnet. What else? It has north and the south poles.
It has a magnetic field.
Magnetic field lines. Can it be increased?
Yes, ma'am.
It can be increased by
Adding
Adding
But
on
not
current,
the
increasing on current
or
or coiling.
Come on, you got quite a lot of points. Come on, write the first point. A solenoid is an electromagnet. Next point. What? Temporary or permanent?
Temporary.
Does it behave like a bar magnet? Yes. It behaves like a bar magnet because it has two poles. Come on, write down that. A solenoid is similar to that of a bar magnet. It has two poles.
Two poles.
And what about the field lines?
They are bad.
From north to south. Right on the next point. The magnetic field lines.
It travels from north to south.
No, I think the magnetic field lines inside the solenoid are in the form of parallel straight lines.
Magnetic field.
Lines inside the solenoid are in the form of parallel straight lines. Okay. In the same point, please write down. This indicates that the magnetic field is the same at all points inside the solenoid. Continue with the same line, that is, the field is uniform inside the solenoid. The field is uniform inside the solenoid. Next point. The strength of the magnetic field can be increased
Or decrease.
no need of decreasing. Everybody wants to increase. And I want you to write down two subpoints. What are these two subpoints? How can you increase?
Adding more
By
current.
adding more.
Increasing current and adding more.
Don't say adding current, read by increasing.
Increasing current.
Right? How can you find out the north, which is the north and which is the south? This is the clockwise. Okay, phase 2. Copy down this diagram because it's not given in your textbook, but it is easy for you to remember. Very good. You can write it as clockwise phase 2. Is that okay? Two minutes. I'm giving you some time to draw the diagram of the solenoid. I need to check it out right now. Invariably, children make mistakes here?
It's the field lines.
Of course, with the payments. Don't draw so many coins because it becomes very confusing. Look at me first. Imagine you're holding, shh, look at me. Take the wire and make 1, 2, 3, maybe 4, and then come down and connect it to the battery. Then you draw the magnetic field lines. Chalo. Quick, quick, quick. Oh, see, there's inside. See here. That is what I said. Everybody will make a mistake. It's going inside the coil. Correct. No, rub it out. First you draw the solenoid, then you draw the magnetic field lines. Wrong. Rub it out. Wrong. See, in spite of telling you so many times, see, everybody is making this mistake. Where are those lines coming from? Rub it out. Ananya, still doing half. Kewa.
Not necessarily wrong.
Enough, just 2, 3 lines. Show the direction. Correct, very good. No, you are the this is okay. You have said things come from inside, no. How is it coming outside the solenoid? The solenoid is behaving like a bar magnet. How about this? This is totally wrong. What have you done? Okay. Maybe we can do a little more. Make it a little more symmetric. Maybe do like this. As long as it's technically correct, it's okay, not otherwise. Sure. Make sure that both of them should be symmetric. Don't make one bigger and one smaller. And that you practice. Is that okay? Show those points. Show those points. Okay. What are you good? Yeah. Okay. Now, there's an in-text question. See this one? Are you looking at the textbook here?
Yes.
Look at the second one. Second one, read the second one, just let me. The magnetic field. Second in text question.
The magnetic field in a given region is uniform. Draw a diagram to represent
Understood the question?
This one.
What are they asking? Did you understand the question?
And
Magnetic, what? Which type?
magnetic field that is in the region of
What's the concept type?
This one.
Yes. They have not used the word solenoid, but they just told that it's a uniform. So we should remember that. Look at question number 3. Look at question 3. Arun, third question.
choose the correct option. The magnetic field inside the long-straight solenoid carrying current A is 0, B decreases as we move towards its end, C increases as we move towards its end, D it is the same at all